Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to start Chapter 7, which looks at redox or reduction-oxidation reactions. In this chapter we're going to go through a lot of sections, although most of them are fairly short, which focus around the reduction-oxidation reactions, which is a new topic we have not looked at yet. The 10 sections will go through what is a reduction reaction, section 1, which we'll cover in this video, oxidation numbers in section 2, and then the application of those oxidation numbers and the rules in section 3. We're then going to look at redox and oxidation numbers in section 4, so how do those oxidation numbers apply to the reactions themselves. We're going to look at some vocabulary in section 5 when it comes to oxidizing agents and reducing agents. We're then going to briefly in section 6 talk about the naming of compounds, because in Cambridge certain names will be different than what we looked at in honors chemistry, and that difference in naming does revolve around oxidation numbers. We're then going to look at how those names can be translated into formulas in section 7. Section 8 is going to be the bulk of this chapter, and it's going to be where the skills that we're going to learn are going to be. When we look at balancing chemical equations using oxidation numbers and something called half reaction method. And then finally in section 9 we'll look at a specific type of redox reaction called a disproportionation reaction. There is a practical associated with this chapter, which is the reduction oxidation titration, which is another kind of titration that uses a natural color change from a reaction to look at concentrations. So let's start with section 1. Section 1 is just going to quickly go over what a redox reaction is. So let's get started. Redox reactions are a combination of two processes that have to happen at the same time: reduction and oxidation. That's where the term redox comes from. It's a mixture of the two terms. So oxidation, reduction are two sides of the same coin. Redox reactions are all about the transferring of electrons from one element to another, or from one species of chemical to another. The term reduction can be viewed in three different ways. Two of these we're going to look at more when we do organic chemistry, and then we're going to focus on the one that's underlined, which is the one for inorganic chemistry. So the term reduction can mean the loss of oxygen by a compound or the gain of hydrogen by a compound. Both of those terms, however, are usually saved or reserved for organic chemistry, where our hydrogen and oxygen are found in plentiful amounts. So we're going to reserve this for organic chemistry. Once we get to section or chapter 14 and forward, then we'll use more of these terms, although it is still something that you should keep in mind that reduction can be defined as the loss of oxygen or the gain of hydrogen. The main issue with these is that we're not always going to have oxygen and hydrogen in every compound that undergoes reduction. And so a better term, a better way of defining reduction, and the proper way of defining reduction when it comes to inorganic reactions, is the gain of electrons. Because we can view redox as the transferring of electrons, reduction in that sense, in that point of view or scope, is going to be the gain of electrons. So when things gain electrons, that is classified as reduction. On the other hand, oxidation is the opposite side of that coin. Oxidation is the opposite process. So in terms of the organic versions of the definitions, oxidation can be seen as the gain of oxygen or the loss of hydrogen. This is because when we originally first discovered reduction and oxidation reactions, when they were first being studied, we mainly discovered them or studied them through processes that both had oxygen and hydrogen. However, we later realized that it's not the oxygen or the hydrogen that play the key role in the process. The process of oxidation is mainly going to happen when an element is losing electrons. So oxidation is the loss of electrons, which is the exact opposite of the reduction process, which is the gain of electrons. Now, why do we call this redox overall? The main reason is because reduction and oxidation cannot happen separately. Reduction is the gain of electrons, meaning those electrons have to come from somewhere. Where do those electrons come from? They come from something that's getting oxidized and it's losing electrons. So that's what we call redox, a transfer of electrons, because we are going from something that is getting oxidized, meaning that whatever compound that is, we'll call it X, is losing electrons. The electrons are leaving X, and then they're going to something that is getting reduced. And since reduction, let's fix that. Since reduction is the gain of electrons, that electron that comes in is coming from somewhere. In this case, it's coming from X, which is getting oxidized. So redox overall, this whole process is called redox or a redox reaction. It's when one element gives up electrons, or it gets oxidized, and another element picks up those electrons, therefore getting reduced. An easy way to remember which one's which one reduction is and which one oxidation is the acronym oil rig. Oil rig, O-I-L-R-I-G, can stand for oxidation is loss of electrons in this case, and reduction is gain of electrons. So oil rig helps us remember which one is gaining electrons and which is losing electrons. Oxidation being the loss of electrons, oxidation is loss, oil, and then reduction being the gain of electrons, or reduction is gain, rig. So let's keep moving forward. Redox reactions, or the two processes, reduction and oxidation, can be viewed in the scopes of what we call a half equation. We can separate any redox reaction into two half equations, one for each of the processes we just discussed. It's an equation which shows either oxidation or reduction only. Now, the difference between a half equation and a regular chemical reaction equation is that when we do a half equation, we are showing electrons. So, in the reduction half equation, because reduction is the gain of electrons, then in the reduction half equation, the electrons are going to act like reactants. For example, this equation right here is an equation that shows the reduction of chlorine. Cl2 gas can gain electrons in order to create two chloride ions, 2Cl- ions. This process is reduction because the chlorine is gaining these electrons. Now, this process does not ever happen by itself because these electrons need to come from somewhere. So paired up with these reactions, there will be an oxidation half equation or an oxidation reaction. The oxidation half equations are also going to show the half process of oxidation, but because it's oxidation, which is the loss of electrons, the electrons are going to be in the products side of the half equation or half reaction. Aluminum solid, for example, can lose 3 electrons, which are here in the products, to give an Al3 plus or aluminum ion. So the half equations show that the distinct process, the reduction, which is the gain of electrons, meaning they're going to be a reactant, or the oxidation, which is the loss of electrons, meaning it's going to be a product. And then these equations can, in a lot of cases, be combined in order to form a full equation, which we'll look at later. sometimes these half equations can be a little more complex than what we see here in these first two whenever they involve a polyatomic ion. Especially true when we have an oxy ion, like permanganate, an ion with oxygen in it. Because whenever we have an oxy ion, we won't just have the element that is changing in oxidation, that is gaining or losing the electrons, like in this case manganese, but we also have oxygen, and that oxygen needs to be balanced out in this equation. Meaning that on the other side of that oxyanion, we'll also have water that is created to balance out the oxygen. Well, that water brings in hydrogen, which means that we also need to have hydrogen ions in the equation on the left side. So this is an example of a half equation for the reduction, and we can tell it's reduction because the electrons are on the left side of a polyatomic ion, and so it is a bit more complex with a few other things playing a role here, like the hydrogen ions and the water. Now, half equations, like I said earlier, can be combined in order to form full equations. We can combine a reduction half equation and a oxidation half equation in order to create a balanced chemical reaction or balanced chemical equation. We do this in two steps. First, let's say we're trying to combine the oxidation reaction of iodide, 2I minus yields I2 plus 2 electrons, with the reduction half equation for the permanganate ion. So this will be the reaction between permanganate and iodide. MnO4 minus plus 8 hydrogen ions plus 5 electrons yields Mn2 plus 4H2O. Well, the first thing we need to do in order to combine these two half equations into a full chemical equation is to make sure that the electrons in both equations match by the smallest number coefficient possible. What does that mean? That means that these two equations need to match because remember that redox is a transfer of electrons. The oxidation half reaction is going to lose those electrons, and the electrons that the oxidation half reaction loses are then carried over into the reduction half reaction to then be picked up by the reduced element and be transformed. Well, in order for this to happen, the number of electrons that are lost by the oxidation reaction need to match the number of electrons that are gained by the reduction. In this case, that's not happening, right? We have 2 electrons in the oxidation given up, 5 electrons in the reduction given up. So what do we need to do here? We need to make these two numbers match by multiplying the whole equation by a whole number. So essentially it's like finding the least common multiple in math. We have 2 electrons here, 5 electrons here. The least common multiple between 2 and 5 is 10. So we want to make both equations have 10 electrons. How do we do this? We simply multiply the equations. How do we get 2I minus yields I2 plus 2 electrons to have 10 electrons? We're going to multiply the whole equation by 5. 2I minus yields I2 plus 2 electrons becomes, when multiplied by 5, 10I minus yields 5I2 plus 10 electrons. Then for the reduction reaction, which has 5 electrons, we're going to multiply the whole reaction by 2 to make it into 10 electrons. This is going to make the two half reactions match, because MnO4 minus plus 8 hydrogens plus 5 electrons, yielding Mn2 plus 4H2O, when multiplied by 2, is going to become 2 MnO4 minus plus 16H plus 10 electrons, yields 2 Mn2 plus 8 H2O. Now that the electrons match, that we have the same number of electrons being given up by the oxidation and fed into the reduction for the reduction to take place, now that those two numbers match, we can do the second step, which is to add the two half equations canceling out anything that appears on opposite sides of the equation. So this is kind of like math when you're combining two equations. If things appear on the same side of the equal sign, you add them up. If they appear on opposite sides, you cancel them out. It's the same thing here. So if we grab the oxidation and the reduction reactions and we add them up, what we are going to do is we're going to cancel out anything that's the same on both sides. Well, in this case, the only thing that's the same on both sides is those 10 electrons. The electrons in the oxidation reaction, the 10 electrons are in the product side, but in the reduction reaction, the 10 electrons are in the reactant side. So when we add these two up, these two are going to cancel. Everything else is unique, so they're going to stay. And so we end up with 2MnO4 minus aqueous plus 10 I minus aqueous plus 16 hydrogen ions aqueous yields, because that's everything in the reactant side, 2Mn2 plus aqueous plus 5I2 aqueous plus 8H2O. So we're just adding up. Anything that doesn't cancel, we're rewriting into our overall equation. That means that when permanganate is reduced and it's combined with the oxidation of iodide ions, this is the overall equation that we end up with. 2MnO4 minus plus 10I minus plus 16 hydrogen ions yields 2Mn2 plus 5I2 plus 8H2O. Now this is actually a bit more complex and there's a more detail to doing these half reaction combinations, but until we get to that section later on, this is as much as you need to know for section 1. Speaking of, that is it for section 1. Thank you for watching. I'll see you in the next video.